All right, let's talk about the invisible forces that are right now holding our entire world together. I mean, everything, from the very chair you're sitting in to the tallest skyscrapers touching the clouds. It's all in a constant, silent battle with physics. So, who's winning?
I mean, have you ever really stopped to think about that? How does a massive bridge just stay up? Or how does a super tall, skinny skyscraper not just get knocked over by a strong gust of wind? It seems impossible, right? But it's not magic. It's a really precise and powerful science that's at work every single second of every single day.
And the answer, the secret sauce to all of this, is something called engineering mechanics. It's basically the rulebook for building anything that needs to be strong, stable, and, safe. So let's dive in and see how it works. To build anything that's actually going to last, engineers can't just force materials to do what they want. No, they have to, they have to understand them. They have to communicate with them, almost like they're learning their language. Think of it like a real conversation. The engineer applies a force to a material, and that material responds. The real trick, the genius of it all, is knowing how to listen to that response and understanding what the material is telling you about its limits. So what are the key words in this language? Well, it all really boils down to two incredibly fundamental ideas: stress and strain. They basically describe the cause and effect of any force on any object.
Okay, first up is stress. When you push, pull, or twist something, the material isn't just a passive observer. It fights back internally. Stress is just the measure of that internal fight spread out across its whole structure. It's the material basically shouting, "Hey, I feel that."
And what happens when a material is under stress? Well, that's where strain comes in. Strain is the physical change you can actually see and measure. It's that tiny little stretch in a steel cable or the microscopic compression in a concrete column. It's the material's physical reaction to the stress it's feeling. Now, this is where things get really interesting, because this is how we define a material's breaking point. First, you've got elasticity. That's when a material can take some stress and then snap right back to its original shape, just like a rubber band. But if you push it too far, it crosses a line. It enters plasticity. And that's when the change is permanent, like when you bend a paperclip and it stays bent. That's the point of no return for a material. So, understanding the materials themselves is one thing, but how do we use them to build these massive structures we see everywhere? Well, it turns out it's not just about what you use, it's all about how you shape it. And that brings us to the truss. You have seen these everywhere, in bridges, in roofs, on construction cranes. The secret to its absolutely incredible strength is hidden in plain sight, the triangle. It's just one of the most stable, most efficient shapes engineers have in their toolbox. It's almost perfect.
And here's why it's so brilliant. A truss takes a big, heavy load and just intelligently splits it up. The top parts get squeezed together, that's compression. The bottom parts get pulled apart, that's tension. Every single little piece has a very specific job to do, and they all work together to make a structure that's unbelievably strong for how much it weighs.
Okay, now let's talk about a force that is so essential we completely take it for granted. It's the force that lets you walk without falling, that lets your car's brakes actually work, and holds nails in the wall. We're talking about friction. Simply put, friction is resistance. It's the grip between two surfaces that fights against any kind of movement. Seriously, without it, the world would just be an impossibly slippery mess. A really cool way to picture friction is with something called the angle of repose. Imagine you're piling up sand, or maybe you've got a book sitting on a tilted board. As you keep increasing that angle, you get to a very specific point, the tipping point, where gravity's pull finally wins the tug of war against friction and things start to slide. That critical angle, that's the angle of repose.
And of course, engineers have a way to calculate this exact moment. The formula looks simple. Fs equals μs times n. Let's break that down real quick. Fs is the max amount of static friction. It's the strongest grip two surfaces can have. And that grip depends on two things. First, μs. That's just a number that tells you how grippy or slippery the surfaces are. And second, n, the normal force, which is just how hard those surfaces are being pushed together. The harder you press, the more friction you get. It's a super powerful way to predict exactly when something is about to slip.
All right, so we've got stress and strain, we have powerful shapes, we understand friction. Let's get to the final section and see how all of this comes together for the most important goal of all: designing things that are safe, things we can literally trust our lives with. To figure out how a real building works, engineers have to simplify how it's connected to the ground. They use three basic types of supports. You've got a fixed support. Think of a flagpole stuck in concrete. It's totally rigid, can't move, can't rotate. Then you have a pin support, which is like a hinge on a door. It lets things rotate freely, but it can't move up or down or side to side. And finally, a roller support, which allows rotation and movement in one direction, kind of like a skateboard on the floor. Every single complex joint in the real world gets modeled using these fundamental building blocks.
When you boil it all down, all the complicated math, all the materials science, all the analysis, it really comes down to this one simple, powerful, non-negotiable rule.
This is it, the core principle of safety. The design action. That's all the bad stuff you can imagine happening. The strongest winds, the heaviest snow, the biggest earthquake. The design strength is what the building can actually withstand. As long as the strength is greater than or equal to the action, the structure is safe. It is the fundamental promise that every single engineer makes.
So, now you have the toolkit, you get the language of stress and strain, you see the genius of a simple truss, and you understand the single most important rule of safety. The invisible world of engineering mechanics is all around you. The only question left is, what will you see differently now?